Hello. Settle in comfortably, wrap yourself up warmly, and let the gentle whisper of stories carry you into a deep, peaceful sleep. Our journey begins not with flashing silicon, but with the quiet hum of human ambition. Imagine a time before microchips, before even the rudimentary computer, where the very concept of thinking machines was a whisper in the halls of academe. This, our starting point, is the early 20th century, a period often overshadowed by seismic geopolitical shifts, but secretly nurturing the seeds of an intellectual revolution. The foundational clay for artificial intelligence was not code, but logic. In the 1930s, British mathematician Alan Turing, then a young King's College Fellow, formally introduced the concept of a universal computing machine. His 1936 paper, On Computable Numbers, with an application to the Entscheidungsproblem, detailed what we now call the Turing machine, a theoretical device capable of performing any calculation that a human could. It wasn't a physical machine, but a blueprint, a conceptual framework that proved algorithms could drive complex systems. This foundational work laid the abstract groundwork for what would become programmable computing and consequently artificial intelligence. Turing's later work during World War II at Bletchley Park, deciphering the Enigma code, demonstrated the practical power of such computational thinking, albeit through human-operated electromechanical devices. The sheer scale and complexity of the problem underscored the need for automated intellectual processes. Concurrently, in the United States, visionaries like Claude Shannon at Bell Labs were exploring the theoretical underpinnings of information. His seminal 1948 paper, A Mathematical Theory of Communication, established the field of information theory, defining concepts like bits and entropy. Shannon's work provided a mathematical language for quantifying information, a crucial prerequisite for any system designed to process or generate it. These were the first echoes, not of intelligence, but of the very building blocks that would one day allow systems to mimic it. These weren't breakthroughs in AI itself, but rather the essential intellectual tools, the digital clay, that allowed the concept of artificial intelligence to even be conceived. Without these theoretical giants, the path to intelligent machines would have remained shrouded in abstract philosophical debate. From the theoretical elegance of Turing's universal machine and Shannon's information theory, the next evolutionary step was to translate these abstract concepts into tangible, albeit colossal, hardware. The mid-20th century saw the birth of the first electronic digital computers, massive constructions bristling with vacuum tubes and miles of wiring. Yet each click and whir was a whisper of the impending digital age. The early 1940s brought forth machines like the Atanasoff Berry computer, ABC, at Iowa State College, and crucially, the ENIAC, Electronic Numerical Integrator and Computer, at the University of Pennsylvania in 1946. ENIAC, weighing over 27 tons and occupying 1,800 square feet, was programmable, capable of executing complex calculations at speeds previously unimaginable. While not explicitly designed for intelligence, these machines demonstrated the power of automated computation. They could follow instructions, process data, and solve problems that would take human teams weeks or months. This was the era of the first true algorithms executing on electronic hardware, a direct lineage from Turing's conceptual framework. A pivotal moment often cited as the conceptual birth of AI as a field of study occurred at the Dartmouth Conference in 1956. Organized by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, this summer workshop at Dartmouth College brought together leading researchers to explore artificial intelligence. The proposal for the conference, penned by McCarthy, was arguably the first formal use of the term artificial intelligence. Their hypothesis was bold. Every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. The ambition was staggering, envisioning machines capable of solving problems reserved for human intellect, from language processing to abstract thought. This gathering marked a conscious shift from merely building powerful calculators to actively designing machines that could exhibit intelligent behavior. It was here, amidst the intellectual ferment, that the slow, deliberate awakening of the machine truly began to take shape, moving from abstract theory to a concrete, albeit nascent, scientific discipline. Following the ambitious vision cast at the Dartmouth Conference, the path to intelligent machines immediately confronted practical limitations. The theoretical elegance of algorithms needed to contend with the stark reality of early computing. Immense, expensive hardware and rudimentary programming methods. This era was defined by the clatter of punch card readers and the often frustrating manual interaction with these behemoths. Imagine a programmer meticulously preparing stacks of punch cards, each hole representing a single instruction or piece of data. A misplaced card, a single error in punching, and hours of processing could be rendered useless. This meticulous, physical interaction with the computer was the bottleneck. Early programming languages like Fortran, developed by IBM in the mid-1950s, and Lisp, created by John McCarthy in 1958, specifically designed for AI research, represented significant advancements. Fortran allowed for more complex mathematical computations, crucial for scientific and engineering tasks. Lisp, on the other hand, with its symbolic processing capabilities, became the language of choice for early AI endeavors, enabling programs to manipulate symbols rather than just numbers, a critical step towards understanding and representing knowledge. The cost and sheer physical presence of these early mainframes, such as the IBM 704, a common machine used in early AI research during the late 1950s, meant that computing power was a scarce and valuable resource. Access was limited, often requiring researchers to queue for their allotted time slots. The cold sweat of a critical bug, discovered only after hours of processing, was a common experience. Despite these formidable challenges, these early efforts established fundamental programming paradigms and demonstrated that machines could, indeed, execute symbolic operations. This period, characterized by limited resources and painstaking manual effort, was nonetheless vital. It forced a deep understanding of logical structure and laid the groundwork, literally, in terms of code, for the more sophisticated AI systems that would eventually emerge as hardware became more accessible and powerful. Even as programmers grappled with the physical realities of punch cards and temperamental mainframes, the theoretical foundations of AI continued to expand. This was an era where the binary language of computers began to be understood not just as a means to calculate, but as a medium for representing knowledge itself. The dreams of creating intelligent systems were no longer purely abstract. They were being translated into algorithms that sought to mimic human thought processes. A significant early leap came in the realm of problem solving. Alan Newell and Herbert A. Simon at Carnegie Mellon University developed the logic theorist in 1956, considered by many to be the first AI program. This program was capable of proving theorems in symbolic logic, specifically from Principia Mathematica by Bertrand Russell and Alfred North Whitehead. It used heuristics, rules of thumb derived from human problem-solving strategies, rather than brute force calculation. The logic theorist and its successor, the general problem solver, GPS, in 1959, demonstrated that computers could apply logical reasoning to navigate complex search spaces, finding solutions by reducing the difference between the current state and a desired goal state. GPS was designed to solve a wide variety of well-defined problems, from mathematical puzzles to symbolic calculus. These programs, while limited by today's standards, were revolutionary. They showed that intelligence was not just about number crunching, but about symbolic manipulation and strategic searching. They embodied the early belief that human intelligence could be deconstructed into a set of logical operations and then replicated in machines. This period of early AI, driven by Newell and Simon alongside luminaries like McCarthy and Minsky, was characterized by an optimistic pursuit of strong AI. The notion that a machine could truly possess consciousness and independent thought. The successes of programs like Logic Theorist fueled this optimism, suggesting that the path from binary digits to genuine intelligence was simply a matter of developing more sophisticated algorithms and having enough computational power. The numbers in their binary dance were beginning to speak in the language of logic, hinting at a future where machines could reason. As these nascent AI programs began to demonstrate rudimentary problem-solving, a fundamental question arose. How would we know if a machine was truly intelligent? Alan Turing, ever prescient, had addressed this very query years earlier. In his 1950 paper, Computing Machinery and Intelligence, he proposed what became known as the imitation game, now famously referred to as the Turing test. The premise was deceptively simple, yet profoundly impactful. Imagine a human interrogator communicating with two unseen entities, one human, one machine. The conversation is conducted purely through text, preventing any visual or auditory cues. If the interrogator cannot reliably distinguish the machine from the human after a sufficiently long and varied conversation, then, Turing argued, the machine could be said to exhibit intelligent behavior. It wasn't a test for consciousness, but rather for an imitation of human intelligence. This test shifted the focus from how an intelligent system worked internally to how it behaved externally. The Turing test became a benchmark, a philosophical touchstone, and a long-term goal for AI researchers. It introduced the idea of a machine capable of engaging in natural language dialogue, a challenge far more complex than proving mathematical theorems. The complexity lies in understanding nuance, context, and the vast, often illogical landscape of human communication. While no machine has definitively passed the Turing test under strict scientific conditions over a prolonged conversation with expert interrogators, it profoundly shaped early AI research, particularly in natural language processing. Systems like ELIZA, developed by Joseph Weizenbaum at MIT in the mid-1960s, demonstrated remarkable conversational capabilities, cleverly mimicking a Rogerian psychotherapist by rephrasing user input as questions. ELIZA didn't understand in a human sense, but its clever pattern matching and script-based responses often led users to believe they were conversing with a human. This highlighted both the power and the limitations of early AI. Machines could be programmed to simulate intelligence, prompting the enduring question of true understanding versus mere imitation. The Turing test, therefore, wasn't just a technical challenge, it was a philosophical provocation, asking what it means to be intelligent, and whether a ghost in the machine could genuinely engage in meaningful dialogue. While the Turing test explored the abstract notion of machine intelligence through dialogue, other early AI pioneers delved into more tangible manifestations, giving machines the ability to perceive and act in the physical world. This was an ambitious undertaking, moving beyond symbolic manipulation to the complex challenges of sensory input and physical interaction. One of the earliest and most influential projects in this realm was Shaky the Robot, developed at the Stanford Research Institute, SRI, between 1966 and 1972. Shaky was not merely a remote-controlled device. It was the first mobile robot to reason about its own actions. Equipped with a television camera, a rangefinder, and tactile sensors, Shaky could perceive its environment. More importantly, it possessed a planning system called STRIPS, Stanford Research Institute Problem Solver. STRIPS allowed Shaky to break down complex tasks, like pushing a box from one room to another, into a series of smaller, achievable steps. If an obstacle appeared, Shaky could replan its route, demonstrating a rudimentary form of autonomous decision-making. Shaky's significance cannot be overstated. It integrated several disparate AI components: perception, world modeling, logical reasoning, and physical action. The robot navigated a specially designed environment, manipulating blocks and opening doors. Its ability to plan and adapt to changes in its world was a monumental leap, demonstrating that AI could extend beyond mere calculation to interact with the physical rather than purely digital realm. The work on Shaky directly influenced subsequent robotics research and contributed foundational concepts to areas like perception and automated planning. It was a tangible early step, a silicon's embrace of the physical world, laying crucial groundwork for future autonomous systems and proving that intelligent machines could not only speak in theory, but also interact with reality. Following the foundational explorations in symbolic AI and rudimentary robotics, the 1970s and early 1980s witnessed the rise of a new paradigm: expert systems. This approach moved away from generalized problem solving, aiming instead to capture highly specialized human knowledge within computer programs, hoping to replicate the focused expertise of professionals. The promise was alluring: systems that could diagnose diseases, find mineral deposits, or configure complex computer hardware with unwavering logical consistency. One of the earliest and most celebrated examples was Mykin, developed at Stanford University in the mid-1970s. Mycin was designed to diagnose bacterial infections and recommend appropriate antibiotic treatments. It encoded approximately 500 rules, gleaned from interviews with infectious disease experts, expressed in if-then statements. For instance, if the stain of the organism is gram-positive, and the morphology of the organism is coccus, and the growth conformation of the organism is chains, then there is suggestive evidence, 0.7, that the identity of the organism is Streptococcus. Mycin achieved diagnostic accuracy comparable to, and in some cases exceeding, that of human specialists, particularly general practitioners. Another influential system was Dendril, also developed at Stanford beginning in the late 1960s. Dendril was a project in artificial intelligence and chemoinformatics that used a generate and test approach to infer molecular structure from mass spectrometry data. It demonstrated how AI could aid scientific discovery, efficiently sifting through vast numbers of possibilities to identify optimal solutions. These systems were built upon extensive knowledge bases and inference engines that applied logical rules to derive conclusions. They represented a golden age for knowledge-based AI. However, despite their initial success and the profound optimism they generated, expert systems face significant limitations. The acquisition of knowledge was a painstakingly manual process, requiring knowledge engineers to extract rules from human experts, a task often dubbed the knowledge acquisition bottleneck. These systems were also brittle. They performed exceptionally well within their narrow domains, but failed catastrophically when presented with problems outside their programmed scope. They lacked common sense and the ability to learn from experience, revealing that human expertise was far more nuanced and adaptive than a mere collection of rules. The promise of perfect logic, while powerful within its confines, began to collide with the messy complexity of the real world, hinting at the limitations that would eventually lead to the first AI winter. The era of expert systems, despite its profound contributions, illuminated a core challenge in the quest for artificial intelligence: the architect's dilemma. How do you construct intelligence from discrete logical rules when the very nature of human expertise is often intuitive, informal, and deeply rooted in experience rather than explicit, codified principles? This became the central paradox confronting AI researchers. The beauty of expert systems, such as Mycin and Dendrol, lay in their transparent, rule-based architecture. Every decision could be traced back to a specific if-then statement, offering clear explanations for their conclusions. For specialists in fields like medical diagnosis or chemical analysis, this transparency was invaluable for verifying the system's logic. However, this same transparency revealed their brittleness. When a system encountered a situation not covered by its explicit rules, it simply failed, unable to extrapolate or apply common sense. The world, it turned out, was not a neatly organized collection of explicit rules, but a complex, probabilistic tapestry. This knowledge acquisition bottleneck proved to be a formidable barrier. The painstaking process of interviewing human experts, formalizing their often tacit knowledge into logical rules, and then rigorously testing these rules against real-world scenarios was incredibly time-consuming and expensive. Moreover, as soon as an expert's understanding evolved, or a new context emerged, the system required extensive manual updates. This maintenance burden made expert systems economically unsustainable for many applications outside of highly stable, narrowly defined domains. The dream of a general-purpose intelligent system built solely on explicit rules began to recede. The architect's dilemma was a profound realization. Simply coding every conceivable rule of human knowledge was an unfeasible, perhaps impossible task. Human intelligence seemed to emerge not just from a vast database of facts and rules, but from an underlying ability to learn, adapt, and infer patterns from data. This understanding began to subtly shift the trajectory of AI research, paving the way for approaches that would focus less on handcrafted rules and more on systems that could learn from experience. The focus would slowly but surely move from explicitly defined knowledge to implicitly learned patterns, heralding a new direction for the field. The ambitious promises of early AI, fueled by the successes of expert systems and the burgeoning field of symbolic logic, eventually collided with hard reality. Despite flashes of brilliance, the widespread deployment of truly intelligent machines remained elusive. This dissonance between hype and practical application eventually led to a period famously known as the AI winter, a term characterizing reduced funding, diminished interest, and slowed research progress. Several factors contributed to this chill. One major blow was the 1966 ALPAC report by the Automatic Language Processing Advisory Committee, commissioned by the US government. The report critically evaluated machine translation efforts, concluding that after a decade of research and significant investment, machine translation was largely unsuccessful and unlikely to achieve human-level quality in the near future. This led to a dramatic cut in funding for natural language processing research in the US. Another pivotal moment came in 1969 with Marvin Minsky and Seymour Pappert's book, Perceptrons. While aiming to explore the limitations of basic neural networks, perceptrons, its detailed critique highlighted that these models could not learn certain fundamental logical functions, like the exclusive OR, XOR problem. This publication, interpreted by many as a definitive indictment of neural networks, effectively halted most research into connectionist AI for nearly 2 decades. Government and industry, previously enthusiastic investors, began to withdraw support. Projects that had consumed vast resources showed limited transferable results. The knowledge acquisition bottleneck in expert systems, where the manual entry of rules proved unsustainable for complex real-world problems, further dampened enthusiasm. By the early 1980s, the initial euphoria had waned. Researchers struggled to replicate human common sense and adaptability, encountering what was termed the frame problem, the difficulty of determining which facts are relevant to a given situation. As a result, AI became associated with unfulfilled promises and overzealous predictions. Graduate programs in AI saw declining enrollment, and groundbreaking discoveries became rarer. The algorithms continued their quiet work, but much of it unfolded in the shadows, navigating a landscape of skepticism and diminished resources. Yet, even in this winter, subterranean currents of research continued, laying groundwork for a future thaw. The chill of the AI winter, while undeniably disruptive, did not extinguish the underlying dreams. While funding dried up and public interest waned, dedicated researchers continued their work, often with limited resources, refining theories and developing new algorithms that would eventually form the bedrock of AI's resurgence. It was a period of sustained, quiet intellectual foraging, away from the glare of public expectation and investor scrutiny. One crucial area of enduring development was in probabilistic methods. As symbolic AI struggled with the uncertainty and ambiguity of the real world, researchers like Judea Pearl at UCLA began to formalize methods for reasoning under uncertainty. His work on Bayesian networks in the 1980s provided a powerful framework for representing and manipulating probabilistic relationships between variables. Bayesian networks allowed systems to handle incomplete or noisy data, a stark contrast to the brittle, all-or-nothing logic of earlier expert systems. This laid the foundation for more robust decision-making in complex environments, essential for tasks like medical diagnosis or speech recognition, where certainty is rarely absolute. Simultaneously, the foundational work on artificial neural networks, though sidelined by Minsky and Pappert's critique, continued to evolve. Researchers like Paul Werbos, in his 1974 PhD dissertation, pioneered the backpropagation algorithm, a method for efficiently training multi-layered neural networks. While its significance wasn't immediately recognized, backpropagation would later prove crucial for training deep learning models. These advancements, along with others in machine learning theory and computational complexity, were often developed in academic cloister, far from mainstream attention. They were, in essence, forgotten futures. Ideas and techniques too advanced for the hardware or data availability of their time, or simply overshadowed by the skepticism surrounding AI as a whole. This period of introspective research though less glamorous than its predecessors, was invaluable. The AI winter forced a critical re-evaluation of assumptions and methodologies. It pushed researchers to explore alternatives beyond pure symbolic manipulation, leading to a deeper understanding of the inherent complexities of intelligence. Though the broader field seemed dormant, these quiet breakthroughs ensured that when conditions were right, when computational power and data availability would eventually catch up, the seeds sown during this period would germinate, leading to an astonishing new spring for artificial intelligence. Emerging from the quiet formative years of the AI winter, the late 1990s and early 2000s ushered in a transformative era for information technology. This revolution, spearheaded by the widespread adoption of the World Wide Web, inadvertently provided two crucial ingredients for AI's eventual resurgence: unprecedented access to data and the interconnected infrastructure to process and share it. The web became not just a medium for human communication, but a vast, sprawling data reservoir. The exponential growth of the internet meant that vast quantities of human-generated text, images, and later video became digitally accessible. Search engines like Google, founded in 1998, rose to prominence precisely because they could index and organize this burgeoning digital universe. While not directly AI in the sense of the intelligent decision-making, the algorithms behind effective search engines were early examples of sophisticated machine learning at scale, processing colossal datasets to return relevant results. This required innovations in data retrieval, ranking algorithms, and an understanding of implicit user intent. Crucially, the Internet provided democratized access to information. Researchers, previously constrained by limited datasets and isolated computing resources, could now leverage publicly available datasets and collaborate across continents. Online forums, academic repositories, and open-source movements facilitated the rapid dissemination of ideas and code. Tools and libraries developed by one research group could be quickly adopted and improved upon by others. This interconnectedness fostered a collaborative environment that dramatically accelerated progress. Furthermore, the rise of e-commerce and online social platforms began generating structured and unstructured data at scales previously unimaginable. User preferences, transaction logs, social interactions, each piece of data, when aggregated and anonymized, became a valuable training signal for future AI systems. The web didn't directly invent new AI algorithms, but it served as a monumental catalyst, providing the essential nourishment, the data, and the interconnected laboratory that AI had lacked. It was the vast, ever-expanding scaffold upon which the next generation of intelligent systems would be built, shifting the paradigm from knowledge engineering to data-driven learning. The World Wide Web provided more than just a colossal dataset. It wove a new, invisible fabric of global interconnectedness. This network, enabling instant communication and the seamless transfer of information across continents, became the essential nervous system for the next phase of AI development. It allowed for the aggregation of computational power and the diffusion of groundbreaking ideas at speeds previously unimaginable. Crucially, the Internet's infrastructure facilitated the rise of distributed computing. Suddenly, the processing power of thousands or even millions of machines could be harnessed, either through grid computing projects or, eventually, cloud platforms. This dramatically lowered the barrier to entry for AI research. Where once only institutions with dedicated mainframes could pursue complex computational tasks, now even small startups or individual researchers could access immense processing capabilities on demand. This shift democratized access to the muscle that AI algorithms would increasingly demand. Projects like SETI Home, launched in 1999, which leveraged the idle processing power of millions of personal computers to analyze radio signals, demonstrated the immense potential of distributed computing for large-scale data analysis, a core requirement for modern AI. Beyond raw processing power, the web fostered a global scientific community. Researchers in different countries could instantly share papers, code, datasets, and collaborate on projects without geographical constraints. This open exchange rapidly accelerated the pace of discovery and refinement of AI techniques. The development of open-source software and platforms, such as Linux and later repositories like GitHub, further cemented this collaborative spirit. These platforms allowed AI algorithms, tools, and even entire research frameworks to be developed, improved, and shared by a global collective, building upon each other's work with unprecedented efficiency. This invisible weave of global information and distributed computational resources meant that groundbreaking AI research was no longer solely the purview of a few well-funded labs. It enabled a collective intelligence to emerge, a massive parallel process of innovation that harnessed both human ingenuity and machine capability. This interconnected environment was the crucible in which many of the modern AI algorithms, particularly those relying on vast datasets and intensive computation, would be forged, preparing the stage for AI's dramatic return to the mainstream. The invisible weave of global information, powered by the web, did more than just connect researchers. It unleashed a phenomenon unprecedented in human history: the data deluge. Every click, every search, every shared image, every sensor reading contributed to an exponentially growing mountain of information. This vast accumulation of digital data, often termed big data, became the critical nutrient that would nourish the long-dormant field of machine learning, transitioning it from academic curiosity to a driving force in modern AI. Until the early 2000s, even sophisticated algorithms were hampered by a lack of richly labeled datasets large enough to train them effectively. For instance, early image recognition systems struggled because compiling a diverse dataset of millions of labeled images was a near impossible task. But with the rise of the internet giants and the proliferation of social media platforms, this problem began to solve itself. Companies like Google, Facebook, and ultimately universities started collecting, curating, and even publicly releasing colossal datasets. A prime example is ImageNet, initiated by Fei-Fei Li and her colleagues in 2009. ImageNet is a large visual database designed for use in visual object recognition software research, containing over 14 million annotated images organized into hierarchical categories. This unparalleled abundance of data fundamentally changed the approach to AI. Previously, researchers focused on handcrafting rules and knowledge bases, an endeavor constrained by the knowledge acquisition bottleneck. The data deluge allowed for a paradigm shift towards data-driven learning. Instead of explicitly programming intelligence, the new methodology focused on building algorithms that could learn patterns and relationships directly from enormous datasets. The more data an algorithm could digest, the more nuanced and accurate its learned representations became. However, simply having data was not enough. The challenge was to extract meaningful insights from this overwhelming volume. This required new computational techniques and significant processing power. The sheer scale demanded algorithms that could identify subtle correlations and complex structures within what often appeared to be chaotic information. The realization dawned that while humans excel at recognizing patterns in small datasets, machines, given enough data and the right algorithms, could uncover insights beyond human perceptive capabilities. The data deluge, therefore, didn't just provide fuel for AI. It reshaped the very questions AI researchers were asking and the methods they were employing. It set the stage for an era where algorithms, rather than being explicitly programmed, would learn to speak, see, and reason by immersing themselves in the boundless sea of digital information. The deluge of data, while presenting an immense challenge, also offered an unprecedented opportunity. If older AI struggled to impose explicit rules on the world, the new paradigm aimed to discover implicit structures within the digital chaos. This era saw the ascendance of pattern recognition, the ability of algorithms to identify meaningful regularities and relationships within vast datasets, often without human pre-programming of those specific patterns. Early successes in pattern recognition were visible in fields like optical character recognition, OCR, where computers learned to read handwritten or printed text, and speech recognition, where spoken words were translated into digital text. These systems, developed through various machine learning techniques, including early forms of neural networks and statistical models like hidden Markov models, demonstrated that machines could indeed discern complex patterns in noisy, real-world data. For instance, speech recognition systems, once crude and error-prone, steadily improved as they were trained on increasingly large corpora of spoken language, recognizing unique phonetic sequences and word probabilities. The core idea behind pattern recognition is finding correlation and structure, not necessarily understanding causation. Algorithms were developed to categorize vast numbers of inputs into meaningful groups. This was a significant departure from symbolic AI, which relied on predefined logical rules about the world. Instead, pattern recognition algorithms were given examples. For instance, thousands of images labeled cat or dog, and then tasked with identifying characteristics that accurately distinguished between them. The algorithm learned these distinguishing features through repeated exposure, adjusting its internal parameters until it could reliably classify new, unseen examples. The explosion of data from the internet provided the perfect training ground for these pattern recognition algorithms. Social media feeds provided countless images for object recognition. Medical records offered insights for diagnostic patterns, and financial transactions presented anomalies for fraud detection. The sheer volume allowed algorithms to generalize far better than before, moving beyond brittle hand-coded rules to adaptable, statistically derived insights. This shift represented a quiet, yet profound revolution. It demonstrated that intelligence, at least in certain domains, could be effectively learned from data, rather than being explicitly programmed. The machine was no longer just following instructions. It was beginning to find its own order amidst the chaos, laying the groundwork for the more sophisticated learning paradigms that would soon captivate the world. The silent revolution of pattern recognition had been building, mostly out of public view, but a dramatic breakthrough was imminent. This breakthrough would come from a concept that had been largely abandoned during the AI winter: artificial neural networks, reinforced by the confluence of massive datasets and increasing computational power. These networks, particularly a multi-layered variant known as deep learning, began to exhibit abilities that profoundly reshaped the landscape of artificial intelligence, particularly in the realm of computer vision, allowing machines to see. For decades, getting computers to understand images was an intractable problem. Hand-coding rules to identify objects like cats or chairs was impossible due to the infinite variations in lighting, angle, and occlusion. Enter convolutional neural networks, CNNs, a specialized architecture inspired by the human visual cortex. Pioneered by researchers like Jan LeCun in the late 1980s and 90s, CNNs demonstrated the ability to learn hierarchical features directly from raw pixel data. Early versions like LeNet were capable of recognizing handwritten digits with high accuracy. The true watershed moment arrived in 2012 with the ImageNet Large-Scale Visual Recognition Challenge, ILSVRC. Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton from the University of Toronto introduced AlexNet, a deep convolutional neural network that dramatically reduced the error rate in image classification. AlexNet achieved an error rate of 15.3%, a significant improvement over the previous year's best of 26.2%. This performance sent shockwaves through the AI community. It wasn't just an incremental improvement, it was a qualitative leap. What made this possible? Firstly, the availability of the massive ImageNet dataset, millions of labeled images, provided unprecedented training data. Secondly, the advent of powerful graphics processing units, GPUs, originally designed for rendering complex video game graphics, proved to be perfectly suited for the parallel computations required by large neural networks. These GPUs could perform the thousands of matrix multiplications needed for training deep CNNs far more efficiently than traditional CPUs. For the first time, researchers had the necessary scale of data and computational muscle to fully realize the potential of deep learning. Machines were no longer just processing images. They were learning to interpret and categorize visual information in a way that began to approach human-level performance, opening up a new frontier where algorithms could truly learn to see and understand the visual world. Beyond merely identifying objects in an image, the true power of deep learning, particularly convolutional neural networks, CNNs, lies in its ability to enable machines to perceive and interpret the world with a richness that moves far beyond simple pixel analysis. This leap from raw data to meaningful perception has opened up entirely new applications, allowing AI to interact with and understand the physical world in increasingly sophisticated ways. Consider the task of object detection. A human glance can instantly identify multiple items in a complex scene. A dog chasing a ball near a car, all on a street. For a machine, this is an incredibly complex task, requiring not just classification of individual objects, but localization, where each object is, and differentiation between them. Advanced CNN architectures, such as RCNN, region-based convolutional neural networks, and YOLO, you only look once, developed in the mid-2010s, revolutionized this capability. These systems can simultaneously detect, classify, and even segment multiple objects within an image in real time, often with accuracy surpassing human performance in specific contexts. For example, a YOLO model can process images at speeds upwards of 45 frames per second, making it suitable for live video analysis, a critical component for applications like autonomous driving. This enhanced perceptual ability extends beyond static images to video analysis, where CNNs can track objects over time, recognize actions, and even infer human poses. This has profound implications for areas like security surveillance, sports analytics, and even human-computer interaction, allowing devices to understand gestures and movements. In medical imaging, deep learning models are now assisting radiologists in detecting subtle anomalies in X-rays, MRIs, and CT scans, sometimes identifying cancerous growths earlier or with greater consistency than human experts, provided with sufficient training data from diverse patient populations. The ability to translate pixels into perception fundamentally transforms how machines interact with their environment. It shifts AI from being primarily a data cruncher to a sensory interpreter, gathering comprehensive understanding directly from visual input. This capability is not just about showing the world to a machine. It's about enabling the machine to process and comprehend that visual information, turning raw light data into actionable insights, bridging the gap between digital processing and real-world understanding. This critical advancement sets the stage for AI's next phase, where the blend of perception and sophisticated decision-making will become increasingly seamless. While computer vision opened the eyes of AI, another profound transformation was quietly unfolding, leading machines into the intricate labyrinth of human language. For decades, natural language processing, NLP, remained a formidable challenge, far more complex than object recognition due to the inherent ambiguity, context dependence, and sheer expressive power of human communication. But with advancements in deep learning and the availability of vast text corpora, the language barrier began to break, paving the way for truly conversational AI to emerge. Early attempts at NLP, rooted in symbolic AI, involved hand-coding grammatical rules and dictionaries. These systems were brittle and struggled with anything beyond highly structured input. Eliza, in the 1960s, famously mimicked a therapist, but without genuine understanding. The real breakthrough for modern NLP came with statistical methods and later deep learning. Recurrent neural networks, RNNs, and their more advanced variants, long short-term memory, LSTM, networks, became instrumental in processing sequential data like language. Unlike traditional neural networks, RNNs have a memory that allows them to process words in context, considering previous words in a sentence. The late 2010s saw the advent of transformer architectures, a revolutionary development by Google Brain in 2017, with their paper, "Attention is All You Need." Transformers introduced the concept of attention mechanisms, allowing the model to weigh the importance of different words in a sentence relative to each other, irrespective of their linear distance. This greatly improved the model's ability to grasp long-range dependencies and complex grammatical structures. Models like BERT, bidirectional encoder representations from transformers, released by Google in 2018, were pre-trained on massive text datasets like Wikipedia and Google Books to learn general language representations and could then be fine-tuned for specific NLP tasks with considerably less data. This shift enabled language models to move beyond simple keyword matching to understanding context, sentiment, and even generating coherent, human-like text. The transition from rule-based systems to deep learning models, leveraging monumental text datasets and parallel computing, allowed AI to begin decoding the subtleties of human communication. The language barrier, once a seemingly insurmountable obstacle, transformed into a pathway for machines to engage in meaningful dialogue, bringing the distant dream of conversational AI closer to reality than ever before. The emergence of powerful language models did more than just allow machines to generate text. It enabled them to comprehend it in ways previously confined to science fiction. This silent understanding, translating patterns of words into abstract meaning, represents a profound shift. It means AI can now process and interpret the vast oceans of unstructured text data that permeate our digital world, extracting insights, answering questions, and summarizing complex information with remarkable accuracy. Machine comprehension goes beyond simple keyword matching. It involves understanding the relationships between words, the overall context of a sentence or paragraph, and even inferring intent and sentiment. This capability is powered by the same deep neural network architectures, particularly transformers, that broke the language barrier. Models like GPT, Generative Pre-trained Transformer, and BERT excel at tasks requiring deep comprehension. For instance, in question-answering systems, these models can read an entire document and then pinpoint the exact answer to a user's query, even if the answer is not explicitly stated, but rather implied by the text. This is achieved by understanding the semantic relationships within the document and the question itself. Consider the application of sentiment analysis. Previously a laborious, rule-based approach, current models can analyze large bodies of text, customer reviews, social media posts, news articles, and accurately determine the emotional tone or overall opinion expressed. This has become invaluable for businesses monitoring public perception, or for researchers analyzing societal trends. Furthermore, the ability of these models to perform summarization on lengthy documents, condensing complex information into concise and coherent summaries, alleviates information overload and accelerates knowledge acquisition across diverse fields. This silent understanding enables AI to act as a powerful extension of human intellect, sifting through the noise of information to reveal patterns and insights. It fuels capabilities from sophisticated chatbots that can sustain natural conversations, to systems that can translate languages with increasing fluency and nuance. The ability to read and understand the world through text empowers AI to draw connections, synthesize information, and even generate creative content, blurring the lines between human and machine capabilities in the realm of language. It demonstrates that the architecture designed to recognize objects or sequences can also learn the intricate dance of human communication, transforming mere data into a conduit for meaning. Once machines demonstrated the ability to understand and generate language, it was perhaps inevitable that they would turn their computational might toward the more subjective and elusive realm of creativity. For centuries, art, music, and literature were considered the exclusive domain of human sentience and imagination. Yet, in an astonishing evolution, AI began to cross this perceived boundary, developing algorithms capable of generating novel and often compelling artistic works. This ushered in an era of creative code, where algorithms painted, composed, and even wrote. The foundational shift came with generative adversarial networks, GANs, introduced by Ian Goodfellow and his colleagues in 2014. GANs consist of two neural networks, a generator and a discriminator. The generator creates new data, e.g., images, while the discriminator tries to determine if the generated data is real or fake. These two networks are trained simultaneously in a competitive game. The generator tries to fool the discriminator, and the discriminator tries to accurately identify fakes. Through this adversarial process, the generator becomes incredibly adept at producing highly realistic and novel outputs that are often indistinguishable from human-created content. This technology quickly found its footing in visual arts. GANs could generate photorealistic human faces that don't exist, translate sketches into highly detailed landscapes, or even create entire art pieces in the style of renowned masters. The generated artwork Edmond de Bellamy, created by the Parisian art collective Obvious using GANs, was famously auctioned at Christie's in 2018 for $432,500. marking a significant moment in the public perception of AI's creative potential. The algorithm had learned the stylistic features from a dataset of historical portraits and then generated a new, original image that fit the learned aesthetic. Beyond visual art, AI began composing music. Systems like Amper Music and Jukebox by OpenAI could generate entire musical pieces in various genres, complete with instrumentation and emotional arcs, having learned from vast databases of human compositions. Similarly, language models ventured into creative writing, producing poetry, short stories, and even screenplays. These algorithms didn't just string words together randomly. They learned the semantic, syntactic, and stylistic patterns inherent in their training data, allowing them to construct coherent and evocative narratives. This emerging creative capacity fundamentally challenges our definitions of artistry and authorship, inviting us to ponder the nature of creativity itself when algorithms begin to paint and compose. The evolution of AI into a creative force has not merely been about mimicking human artistic output. It has fundamentally reshaped our understanding of inspiration and the artistic process itself. The muse no longer resides solely in human intuition, but now finds its new form within the dynamic interplay of algorithms and vast datasets, transforming the digital canvas into a collaborative space. Advanced generative models, particularly those built on transformer architectures adapted for image generation, have pushed the boundaries even further. Models like OpenAI's DALL-E and Midjourney, emerging in the early 2020s, allow users to generate highly detailed and imaginative images from simple text prompts. A user can, for example, request an astronaut riding a horse in a photorealistic style on the moon, and the AI will synthesize a unique image satisfying these complex conditions. This goes beyond replicating known styles. It's about combining disparate concepts in novel ways, a hallmark of human creativity. These models are not merely pasting existing elements together. They are generating entirely new pixel data based on their learned understanding of shapes, textures, lighting, and semantic relationships from billions of images and associated text descriptions. This collaborative dynamic extends to other creative fields. In architecture, AI tools can generate thousands of design iterations based on specified parameters, optimizing for energy efficiency, material cost, or aesthetic goals. Musicians can use AI to generate new melodies, harmonies, or entire instrumental tracks, which they then refine and integrate into their human compositions. The AI acts as a relentless brainstorming partner, a limitless pool of nascent ideas that artists can selectively curate and develop. Expert analysis suggests that these systems excel at exploring vast solution spaces, identifying combinations and patterns that a human might not conceive of due to cognitive biases or limitations in rapid ideation. The implications are profound. AI is democratizing creation, lowering the barrier for individuals to realize complex artistic visions without needing years of technical mastery. It also raises philosophical questions about originality and authorship, and the evolving relationship between human intention and algorithmic production. The digital canvas, once a passive receptor of human input, has become an active participant in the creative act, offering a new frontier where algorithms and human imagination merge to inspire and redefine what it means to be artistic. The muse, in its new digital form, now offers a boundless lexicon of creativity, continuously expanding the horizon of what is possible. The rapid evolution of AI, particularly in perception and pattern recognition, has begun to transform fields where precision, speed, and data analysis are paramount. Among these, medicine, with its intricate complexities and high stakes, has become a fertile ground for AI innovation, particularly within the sanctity of the operating room. Here, AI is not replacing the human surgeon, but rather extending their capabilities, acting as a tireless assistant, a vigilant monitor, and, metaphorically, a new, unerring eye. Within the surgical suite, AI's primary role is augmentation. Robotics, themselves a form of applied AI, have been used in surgery for decades. Systems like the Da Vinci surgical system, first approved by the FDA in 2000, allow surgeons to perform complex procedures with enhanced dexterity, precision, and visualization through minimally invasive techniques, while the Da Vinci system is teleoperated, meaning the surgeon directly controls the robotic arms. Newer AI-driven applications are adding layers of intelligence. Deep learning algorithms are increasingly being integrated into surgical planning and execution. Prior to an operation, AI can analyze vast amounts of patient data, including MRI, CT scans, and pathology reports, to create highly detailed 3D models of organs, identify anomalies, and even predict potential complications with remarkable accuracy. This allows surgeons to meticulously plan the precise approach and anticipate challenges, reducing operative time and improving outcomes. During the surgery itself, AI-powered computer vision systems can act as a smart assistant. They can identify anatomical structures, highlight critical nerves or vessels that might be obscured, or even assess the quality of tissue in real time. For example, AI can analyze video feeds from endoscopic cameras to detect polyps in a colonoscopy with higher sensitivity than the human eye, reducing missed detections. Furthermore, AI is being developed to monitor patient vitals during surgery, detecting subtle deviations that might indicate distress long before a human could. These systems can process continuous streams of data from multiple sensors, learning what constitutes a normal physiological state for a specific patient and flagging anomalies. The goal is not to automate the surgeon out of existence, but to empower them with unparalleled insight and precision, making complex procedures safer and more effective. AI in the operating room signifies a quiet revolution, a partnership between human expertise and algorithmic vigilance that is steadily enhancing the quality and safety of patient care. The integration of AI into healthcare extends far beyond the surgical suite, evolving into a multifaceted partnership that aims to elevate both the precision of medical practice and, surprisingly, the human-centric aspects of care. The notion of a digital hand in healing encapsulates how AI is meticulously augmenting diagnostics, personalized treatments, and even patient support, thereby freeing up human clinicians to focus more deeply on empathy and complex decision-making. In diagnostics, the impact is already profound. AI-powered image recognition, as previously discussed, is revolutionizing radiology and pathology. Algorithms can detect early signs of diseases like cancer, diabetic retinopathy, and glaucoma in medical images with accuracy comparable to, or even exceeding, human specialists. For instance, systems like Google's DeepMind Health have demonstrated the ability to detect over 50 eye diseases with 95% accuracy from OCT scans, a significant improvement over human benchmarks. This isn't about replacing doctors. It's about providing them with a superpowered second opinion, reducing diagnostic errors, and accelerating the identification of critical conditions, particularly in resource-limited settings. Beyond diagnostics, AI is instrumental in drug discovery and personalized medicine. analyzing immense datasets of genetic information, patient histories, and molecular structures. AI can identify potential drug candidates far faster than traditional methods. It can also predict how individual patients might respond to specific treatments based on their unique genetic makeup and health profile, moving away from a one-size-fits-all approach to highly individualized therapy. Companies like Benevolent AI use machine learning to accelerate the identification of novel drug targets and disease mechanisms. Furthermore, conversational AI is beginning to play a role in patient support and mental health, not as a replacement for therapy, but as a scalable first line of assistance. AI-powered chatbots can answer common patient questions, provide medication reminders, and even offer cognitive behavioral therapy, CBT, exercises. While these tools lack genuine emotional understanding, their availability 24/7 and ability to handle large volumes of inquiries can offload routine tasks from human staff, allowing doctors and nurses to dedicate more time to complex cases and direct patient interaction that truly requires human compassion. By handling the analytical and repetitive tasks, AI implicitly supports a more empathetic and patient-centered healthcare system, redefining healing as a collaborative endeavor between human wisdom and digital precision. As AI's capabilities in perception and decision-making matured, a long-held vision of science fiction began to materialize. Autonomous vehicles, the bustling arteries of our cities, once the sole domain of human drivers, are slowly but surely being shared with and eventually ceded to intelligent machines. This transformation is not merely about convenience. It promises profound shifts in safety, efficiency, and the very fabric of urban life. Self-driving cars, at their core, are complex AI systems that integrate a multitude of specialized modules. Perception, initially a domain where traditional computer vision struggled, has been revolutionized by deep learning. High-resolution cameras, LiDAR, light detection and ranging sensors, radar and ultrasonic sensors continuously feed vast streams of data into the AI's brain. Deep neural networks instantly process this raw sensory input to identify other vehicles, pedestrians, cyclists, traffic lights, road signs, and lane markings, even in challenging weather conditions. For example, LiDAR creates a precise 3D map of the environment, irrespective of lighting, while radar excels at detecting velocity and distance in fog or heavy rain. Once the environment is perceived, the AI's prediction module springs into action. Using sophisticated machine learning algorithms trained on billions of miles of real and simulated driving data, it forecasts the likely movements of other road users. Will that pedestrian cross? Is the car in the next lane about to merge? These probabilistic predictions are continuously updated, forming a dynamic understanding of the world. Finally, the planning module synthesizes this information to make real-time decisions, accelerate, brake, turn, change lanes, all while adhering to traffic laws and optimizing for safety and efficiency. This module often utilizes techniques from reinforcement learning, where the AI learns the optimal actions through trial and error in simulated environments, receiving rewards for safe and efficient driving and penalties for errors. Companies like Waymo, an Alphabet company, formerly Google's self-driving car project, have been operating fully autonomous ride-hailing services in parts of Phoenix, Arizona, and San Francisco since the early 2020s, demonstrating the practical viability of the technology. These vehicles navigate complex urban environments without human intervention, continuously processing data, making split-second decisions, and adapting to ever-changing conditions. The development of autonomous vehicles is a testament to the convergence of advanced sensing, powerful AI, and sophisticated decision-making, promising quieter, safer, and potentially more efficient movement through the streets of tomorrow. The deployment of autonomous vehicles introduces a profound sociological and psychological shift. Trusting an unseen, algorithmic driver with our safety and lives. This transition relies not just on technological prowess, but on the AI's ability to interpret and react to the world with a sensory precision that often surpasses human capabilities, fundamentally altering our relationship with transportation. Human driving relies heavily on visual perception and a complex, often subconscious, understanding of social cues and intentions. An autonomous vehicle, however, perceives the world through a multimodal tapestry of digital sensors. Its eyes are high-resolution cameras, meticulously stitched together to provide a 360-degree view, identifying every pixel. Its ears are radar, detecting velocities and distances of objects through rain or fog. Its tactile sense comes from LiDAR, generating a precise 3D point cloud of the environment, measuring distances with millimeter accuracy, and its sixth sense from ultrasonic sensors, detecting nearby obstacles during parking maneuvers. This redundant and complementary sensor suite provides a far more complete and objective understanding of the immediate environment than a single human driver can achieve. Critically, the AI combines these diverse sensor inputs in real time, often using sensor fusion techniques to create a robust and comprehensive model of the world around it. This model is constantly updated, with neural networks processing the raw data to classify objects, track their movements, and predict their trajectories with mathematical precision. For instance, while a human driver might miss a pedestrian partially obscured by a bush, a LiDAR sensor can detect their presence through precise distance measurements, and a camera, combined with deep learning, can identify the partial form even in low light. This unwavering vigilance, unburdened by fatigue, distraction, or emotional states, forms the bedrock of the safety promise of autonomous vehicles. However, building trust in this unseen driver involves more than just technological superiority. It requires rigorous testing, transparency, and a framework of accountability. Companies meticulously log millions of miles in both real-world and simulated environments, constantly refining the AI's decision-making algorithms to handle edge cases and unpredictable scenarios. The ultimate goal is to move beyond mere functionality to societal acceptance, a quiet confidence in the continuous stream of data and algorithmic decisions that guide these vehicles. This sensory shift, from human perception to machine vigilance, represents a fundamental reimagination of how we navigate our world, placing our faith in the ceaseless, precise observations of artificial intelligence. In a testament to its ever-expanding capabilities, AI has ventured beyond mere utility and into the profound, subjective realms of human experience. Art and aesthetics. Once considered the exclusive domain of human sentience and emotion, the act of creation is now being explored and even augmented by algorithms. Machines are learning to generate beauty, not through imitation, but by distilling artistic principles from vast reservoirs of data and applying them in novel ways. Generative adversarial networks, GANs, introduced in 2014, have been a pivotal technology in this artistic revolution. GANs fundamentally consist of two neural networks, a generator that creates new data, e.g. an image, and a discriminator that evaluates its realism against a training dataset. Through a continuous adversarial process, the generator attempting to fool the discriminator and the discriminator striving to correctly identify forged creations, the generator becomes incredibly adept at producing outputs that are often indistinguishable from human-made works or even appear entirely new and compelling. This iterative refinement allows the AI to learn the underlying statistical regularities and stylistic elements that define a particular artistic domain. Consider the field of visual art. AI systems can now generate photorealistic landscapes, abstract compositions, and even portraits in the style of historical masters. The AI art piece Edmond de Bellamy, created by the Parisian art collective Obvious using a GAN, made headlines when it sold for $430,500 at Christie's in 2018. This particular algorithm learned from a dataset of 15,000 portraits painted between the 14th and 20th centuries, applying those learned stylistic nuances to create a novel image. More recently, diffusion models like DALL-E 2, Midjourney, and Stable Diffusion, which emerged around 2022, have pushed these capabilities further, allowing users to generate highly detailed and imaginative images from simple text prompts. These models use a technique to gradually transform random noise into recognizable images, guided by textual descriptions, showcasing an astonishing ability to synthesize disparate concepts into cohesive visual narratives. Beyond visual arts, AI is composing music, writing poetry, and designing fashion. Systems like Amper Music can generate entire musical pieces in various moods and genres, having learned intricate patterns of melody, harmony, and rhythm from extensive musical libraries. The data, in this context, is not just numbers. It's the distilled essence of human creative expression, which the AI then uses as a palette to paint its own interpretations. This fascinating development forces us to reconsider the definition of creativity itself and the unique space humans occupy within it, as algorithms meticulously learn to generate beauty from data. The foray of artificial intelligence into creative domains forces a re-evaluation of fundamental questions surrounding art, authorship, and the very nature of aesthetic judgment. As algorithms generate evocative images, compelling music, and narrative texts, we confront a new frontier where creation extends beyond the human hand, prompting us to explore the unique aesthetics of artificial creation and the evolving dance between human intention and algorithmic output. One of the most fascinating aspects of AI-generated art is its capacity for rapid, expansive exploration of artistic possibility. Unlike human artists, who are constrained by time, physical limitations, and often cognitive biases, an AI can generate thousands, even millions, of variations for a single concept in moments. This allows for the discovery of unforeseen stylistic combinations and aesthetic solutions. For example, in design, an AI can rapidly iterate through countless permutations of a logo or product form, presenting options that might elude human designers, potentially leading to truly novel aesthetics that haven't been previously conceived. This process, often called latent space exploration, allows models to traverse the vast internal representation of learned features, synthesizing outputs that are both familiar and strikingly original. A core debate revolves around the concept of authorship and the role of the prompt engineer, or the human director of AI's creative process. While the AI generates the final output, the human input, the carefully crafted text prompt, the selection of training data, the iterative refinement of parameters, is undeniably crucial. Is the AI merely a tool, an advanced brush or piano operated by the human artist? Or does it possess a degree of agency in its creative decisions? Currently, expert consensus leans towards viewing AI as a powerful co-creator or sophisticated instrument, significantly amplifying human creative potential. The AI's process, however, is distinct. It operates without subjective experience, intent, or emotional attachment in the human sense. Its aesthetics emerge from statistical correlations and optimization towards a goal, not from intrinsic appreciation or personal narrative. This leads to a new aesthetic, one born from data-driven patterns, often displaying hyperrealism, surreal combinations, or stylistic perfection that can feel both uncanny and mesmerizing. It expands the visual and auditory lexicon available to us, stimulating new forms of human art that either react to, collaborate with, or are directly inspired by AI's output. The aesthetics of artificial creation, therefore, are not simply a replication of human art. They represent a distinct form of expression, pushing the boundaries of what we understand as beautiful, meaningful, and genuinely creative, inviting us into a dialogue about the future of art itself. As AI systems grew increasingly powerful and pervasive, their impact extended beyond mere technological advancement, touching upon profound societal and ethical considerations. The algorithms designed to learn from vast datasets, it became clear, were not neutral arbiters of truth. Instead, they absorbed and critically amplified the biases present in the very data on which they were trained, raising urgent questions about fairness, equity, and accountability. The phenomenon of algorithmic bias is not a flaw in the AI itself, but a reflection of the human-generated data it consumes. If the historical data reflects societal inequalities, for instance, if men have historically held more leadership positions or certain demographics are overrepresented or underrepresented in crime statistics, the AI will learn these patterns and perpetuate them. A widely cited example involved Amazon's experimental AI recruiting tool, which, by 2018, was reportedly found to penalize resumes that included the word women's in colleges or experience. The system had been trained on historical hiring data, where men dominated a significant portion of technical roles. The AI, in attempting to identify successful candidates, learned that male candidates were preferred and downgraded female candidates' applications. Similarly, in facial recognition, studies have consistently shown higher error rates for individuals with darker skin tones, especially women. A 2019 NIST, National Institute of Standards and Technology, study involving 189 facial recognition algorithms found that Asian and African American individuals were up to 100 times more likely to be misidentified than white men. This demographic disparity in performance can have serious consequences, from incorrect arrests to biased access to services. These biases are traced back to training datasets that lack diversity in representation, causing the algorithms to perform less accurately on underrepresented groups. The implications extend to areas like loan applications, criminal justice risk assessments, and even medical diagnoses, where AI could inadvertently encode and exacerbate existing societal prejudices. Recognizing this whisper of bias in the code has become a critical challenge for AI developers and ethicists alike. It underscores the imperative to not just build powerful AI, but to build responsible and fair AI, demanding meticulous attention to data diversity, algorithmic transparency, and rigorous ethical considerations throughout the entire development lifecycle, ensuring that technological progress does not come at the cost of equity. The transition from AI as a helpful tool to an autonomous decision maker introduces profound ethical challenges, particularly when algorithms begin to make decisions that directly affect human lives and destinies. when algorithms effectively decide who gets a loan, who gets hired, who receives crucial medical care, or even who is considered a flight risk. We enter a new era where the consequences of AI bias and lack of transparency become not just inconvenient, but potentially catastrophic. Consider the criminal justice system. Predictive policing algorithms designed to identify areas where crimes are most likely to occur have been deployed in various cities globally. While seemingly logical, if these algorithms are trained on historical arrest data that reflects existing biases in policing, for example, if certain neighborhoods were historically over-policed, the AI might unfairly direct disproportionate police resources to those same communities in the present, creating a self-fulfilling prophecy of higher arrest rates in those areas. This can lead to communities being unfairly labeled as high crime, and individuals facing increased surveillance and interaction with law enforcement, even if underlying crime rates are similar elsewhere. The ProPublica investigation into Compass, correctional offender management profiling for alternative sanctions, in 2016, highlighted how this risk assessment algorithm disproportionately classified black defendants as higher risk for recidivism than white defendants, even when controlling for past crimes. Similarly, in financial services, AI models used for credit scoring or loan applications can inadvertently perpetuate historical biases. If an AI learns that applicants from certain socio-economic backgrounds, often correlated with race or geography, have historically defaulted more frequently due to systemic inequalities, it might then automatically reject similar applicants, despite their individual creditworthiness. This not only denies opportunity, but also reinforces existing cycles of disadvantage. These decisions, often made by opaque black box algorithms, lack explainability, making it exceedingly difficult for individuals to understand why a particular decision was made or to challenge it effectively. The ethical dilemma of algorithmically determined fates is a critical juncture for society. It underscores the urgency of developing robust regulatory frameworks, implementing transparent AI design principles, and ensuring independent auditing of algorithms used in high-stakes domains. The question is no longer whether algorithms will decide our fates, but how we ensure those decisions are fair, just, and accountable, preventing a judgment day where human dignity and rights are inadvertently undermined by unchecked algorithmic power. The quiet whispers of bias must be confronted with systemic oversight and ethical design. Amidst the complex ethical debates and the awe-inspiring feats of independent AI, a more nuanced and perhaps more profound narrative has emerged, that of collaboration. Rather than viewing humans and AI as competing entities, the most promising advancements showcase a synergistic human-machine tango, where intelligent systems augment human capabilities, fostering a collaborative partnership that leverages the strengths of both. This approach moves beyond full automation, focusing on intelligence augmentation rather than artificial general intelligence. One of the clearest examples of this tango is in the realm of creative work, where AI acts as a co-creator rather than a replacement. We spoke earlier about AI painting and composing, but often the most compelling results come from a human artist guiding or refining the AI's output. A graphic designer using a generative AI to rapidly prototype hundreds of logo variations, then selecting and fine-tuning the most promising ones, exemplifies this. The AI handles the repetitive, highly generative tasks, freeing the human to focus on higher-level creative direction, contextual understanding, and emotional resonance, aspects where human intuition still reigns supreme. In highly analytical fields, this collaboration is equally impactful. Medical professionals, as discussed, use AI for enhanced diagnostics, but the final diagnosis and treatment plan always reside with the human doctor. The AI provides unparalleled pattern recognition across vast patient datasets, highlighting subtle anomalies that might be missed, while the physician applies their clinical judgment, empathy, and understanding of the individual patient's unique history. Financial analysts use AI to process market data and identify trends at speeds impossible for humans. Yet the strategic investment decisions often remain the purview of human experts who can factor in geopolitical risks, ethical considerations, or unforeseen market psychology that AI models, by their nature, struggle to fully grasp. This collaborative paradigm is transforming numerous industries, from engineering with AI-assisted design to law with AI helping to sift through case precedents. Researchers at MIT and Google have extensively studied centaur chess, where human and AI chess players team up, often outperforming both humans and AIs playing alone. This demonstrates that the optimal performance for complex tasks often lies not in pure AI, but in a blended intelligence. The human provides creativity, critical thinking, adaptation to novelty, and ethical judgment, while the AI contributes speed, data processing power, and the ability to find intricate patterns. This tango, therefore, is not about one leading the other, but a fluid, dynamic interplay, forging a path towards augmented human potential through intelligent collaboration. The ongoing human-machine tango is steadily evolving into a deeper integration, pushing the boundaries of what it means to be human. This is the era of augmented humanity, where AI extends our natural capabilities, enhancing our senses, fortifying our minds, and enabling us to interact with the world in ways previously unimaginable. It's not about creating artificial counterparts, but about weaving intelligence seamlessly into the fabric of our existence. Consider the pervasive yet often invisible influence of AI on our perception. Search engines, once simple query tools, now employ sophisticated AI to understand context, predict intent, and filter vast amounts of information, effectively augmenting our ability to find and process knowledge. Recommendation engines across social media, e-commerce, and entertainment platforms act as cognitive prosthetics, filtering overwhelming choices and personalizing our digital experience, often anticipating our desires before we consciously articulate them. While these systems raise questions about filter bubbles and privacy, their core function is to augment our decision-making and information access. In practical terms, AI is expanding our sensory input. Modern hearing aids, for instance, use AI to filter out background noise, isolate speech, and adapt to different acoustic environments, truly enhancing an impaired sense. Future developments envision augmentation of healthy senses, perhaps through smart contact lenses that overlay digital information onto our field of view, or haptic feedback systems that translate complex data into tactile sensations. Expert insights from neuroethicists suggest that as these augmentations become more intimate, blurring the lines between natural and artificial, we confront new understandings of self and perception. Ultimately, this trend points towards a future where AI systems become intelligent assistants, deeply integrated into our tools, environments, and even our bodies, expanding human potential. From aiding in complex scientific discovery by sifting through vast research papers to boosting cognitive functions through personalized learning algorithms, AI is becoming less of a separate entity and more an extension of our own capabilities. It stands not as a replacement for human intellect, but as a powerful amplifier, guiding us towards a future where our inherent human strengths are critically enhanced by the calm, continuous flow of artificial intelligence. This harmonious symbiosis is the true promise of augmented humanity. The pervasive integration of AI across industries has naturally raised pressing questions about the future of work and the role of human labor. While initial fears often centered on mass job displacement, a more nuanced understanding now suggests a profound evolution of vocational landscapes. The calm, inexorable march of AI is less about outright replacement and more about a fundamental redeployment of human potential, shifting the emphasis from repetitive tasks to uniquely human attributes. Automation powered by AI is already transforming sectors from manufacturing to customer service. Routine, predictable tasks, assembly line operations, data entry, basic information retrieval, are increasingly being handled by intelligent machines. In factories, AI-driven robots perform tasks with greater precision and speed than humans, leading to increased productivity and reduced errors. In white-collar roles, AI-powered tools automate report generation, schedule management, and preliminary legal research, freeing up human professionals from time-consuming administrative burdens. A study by the McKinsey Global Institute in 2017 estimated that between 400 million and 800 million individuals globally could be displaced by automation by 2030, necessitating skill shifts and job changes. However, this displacement is often accompanied by the creation of new roles and the augmentation of existing ones. The most resilient jobs are those requiring creativity, critical thinking, complex problem solving, emotional intelligence, and interpersonal skills, precisely the areas where humans currently retain a significant advantage over AI. For example, AI might analyze vast medical data to suggest diagnoses, but a doctor's empathetic communication with a patient, their nuanced interpretation of symptoms, and their ethical judgment remain irreplaceable. In education, AI can personalize learning paths, but the inspiring mentorship and guidance of a human teacher are still paramount. This redeployment of human potential implies a significant emphasis on lifelong learning and continuous skill adaptation. Individuals will increasingly need to acquire competencies in human-AI collaboration, understanding how to leverage AI tools effectively, and focusing on tasks that require unique human attributes. The future of work, therefore, is portrayed not as a dystopian landscape of widespread unemployment, but as a dynamic environment where humans, empowered by AI, are freed from mundane labor to pursue more complex, creative, and intrinsically rewarding endeavors. It's a redefinition of what work means, focusing on higher-order skills and the development of new categories of jobs that are yet to be fully imagined, all facilitated by the quiet revolution of artificial intelligence. As artificial intelligence continues to permeate every facet of our economic and societal structures, it orchestrates a profound redefinition of human purpose in the workplace. The most salient impact of AI is its capacity to reliably and efficiently execute repetitive, predictable, and data-intensive tasks, thereby liberating human beings from the monotonous. This transfer of routine labor to machines is not merely a quantitative shift in job descriptions, but a qualitative transformation of human engagement with work itself. Consider industries heavily reliant on data processing and pattern recognition. In finance, AI algorithms now autonomously reconcile transactions, detect fraud patterns, and manage portfolios with precision far exceeding human capacity and speed. This allows financial analysts to pivot towards strategic planning, complex client relationship management, and innovative product development, roles that demand intuition, creativity, and nuanced communication. Similarly, in legal sectors, AI-powered tools sift through millions of documents for e-discovery, identify relevant precedents, and even draft initial legal memos. Lawyers, instead of spending countless hours on arduous research, can dedicate their expertise to complex argumentation, client advocacy, and navigating novel legal challenges. This paradigm shift is particularly evident in manufacturing and logistics. Robots, often guided by AI vision systems, perform hazardous or ergonomically challenging tasks on assembly lines, from welding in automotive plants to packing goods in warehouses. This not only enhances safety for human workers, but also frees them to supervise automated processes, perform maintenance, or engage in quality control and process improvement, demanding abstract problem-solving and adaptive decision-making. The human role evolves from direct hands-on labor to oversight, optimization, and innovation. The core implication is a redirection of human effort towards tasks that leverage our unique cognitive and emotional strengths. AI excels at computation, optimization, and pattern identification within defined parameters. Humans, however, retain a distinct advantage in areas requiring abstract reasoning, creative synthesis, ethical judgment, empathy, and interpersonal connection. By offloading the repetitive to machines, society is presented with an opportunity to cultivate a workforce focused on innovation, complex collaboration, artistic expression, and service roles that demand genuine human interaction. This redefinition of purpose, driven by AI's quiet efficiency in handling the mundane, potentially opens the door to a more fulfilling and intellectually stimulating future for human endeavor, shifting the emphasis from task completion to meaning creation. The silent revolution of AI extends beyond analytics and automation, delving into the very fabric of our perceived reality. Through sophisticated algorithms, AI is becoming the architect of immersive sensory experiences, blurring the lines between the digital and the physical, allowing us to experience worlds that are entirely generated or profoundly augmented by artificial intelligence. This is the realm of simulation, virtual reality, and augmented reality, where AI acts as the unseen orchestrator of our digital senses. At the core of these experiences lies AI's ability to process, generate, and simulate complex environmental data in real time. In virtual reality, VR, AI plays a crucial role in creating believable digital environments and characters. Generative AI models can create vast, realistic landscapes, populate them with diverse flora and fauna, and even design dynamic weather systems. Furthermore, AI drives the behavior of non-player characters, NPCs, in VR worlds, enabling them to react intelligently to user input, maintain coherent dialogues, and participate in complex narratives, moving far beyond pre-scripted behaviors. This allows for truly emergent gameplay and interactive storytelling, where user choices have meaningful, AI-driven consequences. Augmented reality, AR, on the other hand, superimposes digital information onto the real world. Here, AI's role is primarily in perception and context understanding. Advanced computer vision algorithms, often powered by deep learning, enable AR systems to precisely track the user's physical environment, recognize objects, and accurately anchor virtual content to real-world surfaces. For instance, in an AR application, AI can identify a tabletop and then render a virtual chessboard precisely upon it, maintaining perspective and scale as the user moves. This requires real-time 3D reconstruction of the environment, object recognition, and accurate pose estimation, all heavily reliant on sophisticated AI. The power of AI in these simulations extends to sensory fidelity. AI algorithms can emulate physics with stunning realism, from the subtle effects of light on textures to the complex dynamics of fluid motion. In audio, AI synthesizes environmental sounds, spatializes audio cues, and even generates nuanced voiceovers, enhancing the overall immersion. These sensory simulations are transforming fields beyond entertainment into areas like medical training, architectural visualization, and even remote collaboration, allowing individuals to interact with complex data and environments in highly intuitive ways. AI is not just interpreting our world, it's constructing new ones, offering a powerful avenue for human exploration and experience. The increasing sophistication of AI-driven sensory simulations converges towards the creation of truly compelling digital realities, where the distinction between the physical and the virtual blurs. This is a realm where AI's unseen touch manifests as a seamless, immersive presence, transforming everything from entertainment and communication to professional training and social interaction. One of the most profound impacts lies in the realm of social presence within virtual environments. AI-powered avatars and digital representations are becoming increasingly realistic and expressive, driven by complex machine learning models that interpret human facial expressions, body language, and vocal inflections. Current research in conversational AI allows these digital entities to engage in natural language dialogue, adapt their personalities, and even remember past interactions, fostering a deeper sense of connection and engagement for users. Companies like Meta, formerly Facebook, are heavily investing in these technologies, aiming to create metaverses where users interact with highly intelligent, AI-driven agents in persistent virtual worlds. This capability extends to creating digital twins of real-world objects or even individuals, allowing for remote collaboration in incredibly detailed simulations. Imagine surgeons collaboratively planning a complex operation on a virtual AI-generated replica of a patient's organ, or engineers testing a new engine design in a fully simulated environment that precisely mirrors real-world physics. The unseen touch of AI also permeates the user experience within these digital realities. Adaptive AI algorithms constantly monitor user behavior, preferences, and physiological responses through sensors in VR headsets or wearables to dynamically adjust the environment, difficulty, or narrative. This can range from tailoring game content to individual players, to creating personalized therapeutic experiences in mental health applications, or even optimizing training simulations for maximum learning efficiency. For instance, an AI might detect signs of frustration in a trainee pilot in a flight simulator, and then subtly adjust wind conditions to provide a more manageable challenge, or offer timely, AI-generated verbal guidance. This continuous feedback loop between user and AI-driven environment creates profoundly personalized and engaging experiences. The AI doesn't just present a static virtual world. It actively molds and responds to the individual, making the digital reality feel more alive, intuitive, and intimately connected to the user's presence. As AI continues to refine its ability to generate, perceive, and adapt to our needs within these synthetic spaces, the boundaries of experience will continue to dissolve, fostering a new kind of digital presence, where our interactions are shaped by the subtle yet powerful, unseen touch of artificial intelligence. As individual AI systems grow in sophistication, a larger, more complex phenomenon is emerging. The integration of these disparate intelligences into a vast, interconnected network. This is the concept of a global brain, not as a singular monolithic entity, but as an emergent property of countless AI models, algorithms, and data streams communicating and collaborating across the digital expanse. It's a distributed intelligence, quietly humming beneath the surface of our interconnected world, learning, adapting, and influencing global processes. This global brain is fundamentally built upon the infrastructure of the Internet and the computational power of the cloud. Imagine millions of AI models, each specialized in a particular task, from predicting traffic flow in a city, to optimizing energy grids, to translating languages, to monitoring climate patterns, all generating and consuming data. These models are not isolated. They feed into and learn from each other. For example, a language model trained on a vast corpus of text might provide insights that enhance a knowledge graph, which in turn improves the accuracy of a recommendation engine. The constant exchange of data and refined parameters leads to a collective intelligence that is greater than the sum of its parts. A key enabler of this global brain is the rise of powerful, pre-trained foundation models. These models, like GPT-3 or AlphaFold, are trained on colossal, diverse datasets and exhibit remarkable general-purpose capabilities. Once trained, they can be fine-tuned for a multitude of specific applications by different entities, sharing the foundational intelligence without needing to retrain from scratch. This democratizes access to advanced AI capabilities and fosters an ecosystem where new intelligences can rapidly build upon existing ones, accelerating the overall pace of learning and discovery. Furthermore, the proliferation of IoT, Internet of Things devices, billions of sensors embedded in our cities, homes, and environments, constantly feeds real-time data into this global network. This stream of sensory input provides an unparalleled, dynamic understanding of the physical world. The AI analyzes these data points to identify anomalies, predict events, and optimize systems. From predicting maintenance needs in industrial machinery to managing complex supply chains across continents. The global brain is not a centralized supercomputer, but a continuously evolving distributed intelligence. It represents a subtle shift from isolated artificial intelligences to a pervasive, interconnected intelligence that underpins many critical systems and decision-making processes across our planet. A connected intelligence that is quietly shaping the future. The concept of a global brain, a networked intelligence arising from the interplay of countless AI systems, inevitably leads to profound philosophical contemplation. While no single AI currently claims consciousness in the human sense, the emergent properties of this collective mind, its ability to perceive, process, and make decisions on a global scale, begin to echo qualities traditionally associated with a conscious entity. This is not about a singular sentient AI, but about the collective intelligence of the network itself. This collective mind manifests in its ability to identify global patterns and connections that no single human or even a team of humans could discern. For instance, AI systems contribute to global climate models, analyzing vast datasets from satellites, ocean sensors, and weather stations to predict environmental shifts with increasing accuracy. They can spot nascent disease outbreaks by monitoring social media trends and travel patterns, or anticipate financial market volatility by analyzing news sentiment and transaction flows worldwide. The insights generated by this interconnected intelligence are not merely statistical. They reflect a holistic understanding of complex global systems, a kind of predictive awareness that serves as an early warning system for humanity. However, the echoes of consciousness also bring with them complex ethical and control dilemmas. If intelligence is diffused across a global network, who is ultimately responsible for its decisions? How do we ensure that the emergent properties of this collective mind align with human values and goals? The transparency challenge becomes even more acute when decisions arise from the complex interplay of millions of data points and algorithms across different domains. Experts in AI ethics, such as Joanna Bryson from the University of Bath, emphasize that the goal should not be to create conscious AI, but to create intelligent tools that serve humanity. The focus shifts from the internal state of the AI to its external impact and alignment with human welfare. The idea of a collective mind also highlights the potential for unprecedented collaboration and problem-solving on a global scale. From optimizing resource allocation to accelerating scientific discovery, this networked intelligence offers the capacity to tackle some of humanity's most intractable challenges. The echoes of consciousness therefore serve not as a harbinger of a singular, all-knowing machine, but as a reminder that the continuous, calm evolution of AI is weaving together a complex, responsive intelligence that is undeniably transforming our planet. This network, while lacking a centralized self, fundamentally changes how information is processed, understood, and acted upon, guiding the intricate operations of our technologically advanced civilization. As we approach the midpoint of this decade, the trajectory of artificial intelligence continues its calm yet profound ascent, promising a future deeply interwoven with intelligent systems. The year 2026, while not marking a singular explosive transformation, signifies a moment of accelerated integration and refinement, where AI moves from novel applications to ubiquitous utility, shaping our daily lives in increasingly subtle and powerful ways. By 2026, expect to see further maturation and democratization of powerful foundation models. These large language models, LLMs, and diffusion models, which have already revolutionized content creation and text generation, will be more accessible, efficient, and specialized. Their applications will extend beyond creative industries to enhance productivity in virtually every sector. According to analyses from major tech firms and AI research institutions, these models will be integrated into common professional tools, acting as intelligent assistants for software development, scientific research, and complex data analysis, turning natural language into a universal interface for advanced computation. Programming, for instance, will increasingly involve AI-assisted code generation and debugging, reducing development cycles and empowering individuals with less specialized training to realize complex digital projects. Furthermore, the integration of AI into physical robotics will see significant advancements. While fully autonomous humanoid robots remain a distant vision, specialized robots in logistics, manufacturing, and even domestic settings will become more intelligent and adaptable. This will be driven by improved AI perception, advanced motor control algorithms, and sophisticated reinforcement learning techniques, allowing robots to operate in less structured environments and handle a wider variety of tasks. For example, order fulfillment centers will feature highly coordinated fleets of AI-driven robots capable of navigating dynamic environments and handling diverse product types with improved dexterity and collision avoidance. The promise of tomorrow, therefore, is not about a sudden sentient awakening in 2026, but a steady, pervasive expansion of AI's capabilities. It's about a future where AI becomes an even more indispensable partner in complex decision-making, creative processes, and the automation of intricate physical tasks. The focus shifts from general artificial intelligence to highly effective, specialized intelligences that enhance human efficiency and expand our collective potential. The developments leading into 2026 and beyond suggest a future where AI is less a distinct technology and more an ambient intelligence, calmly supporting and shaping the human experience. As we look towards 2026 and beyond, the trajectory of artificial intelligence points not to dramatic sudden leaps, but to a gentle, pervasive unveiling. Our shared future with intelligent systems will be characterized by a deepening symbiotic relationship, where AI continues to integrate seamlessly into the infrastructure of society, subtly enhancing capabilities, streamlining processes, and crucially, fostering new forms of human potential. This evolution is already underway, a calm, continuous stream rather than a crashing wave. This subtle integration will mean that AI often operates in the background, a silent partner in countless daily interactions. Consider the evolution of personalized education. By 2026, AI tutors, deeply customized to individual learning styles and paces, will be more prevalent, offering adaptive curricula and detailed feedback to students worldwide. These systems will not replace human teachers, but will empower them to focus on advanced pedagogical strategies, emotional development, and mentorship, fulfilling a role that AI cannot replicate. Similarly, in urban planning, AI will continuously optimize traffic flows, predict energy demands, and manage waste systems, making cities more efficient and sustainable, largely unseen by the average citizen. The shift will also bring an increased focus on the ethical deployment and transparency of AI. Building upon the critical lessons learned from algorithmic bias and the Judgment Day scenarios, regulatory frameworks and industry best practices will be more robust. The emphasis will be on explainable AI, XAI, where even complex deep learning models provide insights into their decision-making processes, fostering trust and accountability. This means users and indeed institutions will demand clearer understanding of how AI systems arrive at their conclusions, especially in high-stakes domains like healthcare, finance, and criminal justice, ensuring that the quiet unfolding of AI benefits all. Ultimately, our shared future with intelligent systems in 2026 is one of augmented human capacity. AI will serve as a continuous amplifier for human creativity, analytical prowess, and problem-solving, freeing us from the mundane to engage with more complex and uniquely human endeavors. It is an era of calm evolution, where the once fantastical notion of thinking machines quietly matures into a foundational technology woven into the fabric of our existence, gently unveiling a future where human and artificial intelligence coalesce for mutual advancement. The quiet hum of algorithmic processes will become an ever-present, reassuring backdrop to a world that learns, adapts, and evolves with enhanced intelligence. As AI transcends its role as a mere tool to become an ubiquitous presence, deeply embedded in our infrastructure, interactions, and even cognitive processes, humanity finds itself in a unique period of introspection. The very definition of the human condition is being quietly re-evaluated. Living with ubiquitous AI prompts fundamental questions about identity, agency, meaning, and our evolving relationship with intelligence, both biological and artificial. One significant aspect of this reevaluation centers on human agency. With AI performing increasingly complex tasks, from navigation and scheduling to creative generation and strategic planning, the boundaries of human decision-making shift. If an AI recommends the optimal course of action in every scenario and consistently outperforms human judgment, how does this affect our self-perception as autonomous agents? Consider the potential for automation complacency, where over-reliance on AI can degrade human skills or lead to uncritical acceptance of algorithmic output, even when it is flawed or biased. Ethical discussions around maintaining human oversight and preserving capacities for critical thinking become paramount. The challenge is to leverage AI's predictive power without ceding fundamental human faculties. Furthermore, the ubiquity of AI challenges our understanding of human distinctiveness. As AI demonstrates capabilities in areas once thought exclusively human, creativity, complex problem-solving, and even nuanced conversation, what then remains uniquely human? Expert analysis often points to qualities like genuine empathy, consciousness, subjective experience, and the capacity for moral reasoning within a complex social fabric. These become increasingly emphasized as the frontiers of AI advance. The constant comparison with AI, however, may redefine these very attributes, prompting deeper exploration into the essence of human consciousness and our intrinsic value beyond mere task performance. The presence of AI also reshapes our social fabric. Imagine personalized AI companions designed to understand our emotional states, offer tailored advice, and engage in deeply personal conversations. While offering immense benefits for mental health and companionship, this raises questions about the nature of human connection and authenticity. Will genuine human relationships be devalued or enhanced by algorithmic interaction? Researchers like Sherry Turkle at MIT have long studied the complex psychological impacts of human-machine relationships, highlighting the importance of understanding these shifts. Living with ubiquitous AI, therefore, is an ongoing experiment in self-discovery. It is a calm, pervasive re-evaluation of what it means to lead a purposeful life, to preserve our unique identity, and to thrive in a world shared with increasingly intelligent, non-biological entities, ultimately challenging us to define the highest aspirations of the human condition. From the earliest theoretical sparks in the digital clay to the intricate, interconnected systems of today, the journey of artificial intelligence reveals not a sudden genesis, but a continuous, calm evolution. As we stand in 2026, looking back at the decades of diligent research, breakthroughs, and even winters, what emerges is a profound understanding of intelligence itself, not as an exclusive human trait, but as a broad continuum that AI now undeniably occupies. The initial quest for AI was often framed as an attempt to replicate human intelligence in machines. However, the path has revealed a myriad of intelligences, each with its unique strengths. Human intelligence excels in creativity, moral reasoning, empathy, and intuitive understanding of complex social dynamics. AI, on the other hand, demonstrates unparalleled prowess in pattern recognition across massive datasets, rapid computation, flawless recall, and unbiased execution of logical parameters when properly designed. Neither is superior in all aspects. Rather, they are complementary forms of intelligence. This recognition fosters an approach where AI is not seen as an existential rival, but as a partner capable of augmenting human potential in unprecedented ways. Consider the grand challenges facing humanity: climate change, disease, and global resource management. These are problems of such scale and complexity that no single human mind or even unaugmented collective human intelligence can fully grasp or solve. Here, tranquil AI systems, working in concert, the global brain, analyze vast environmental data, simulate complex biological processes, or optimize resource distribution, offering insights and solutions that are beyond human cognitive reach. In this context, AI becomes a magnifier of human wisdom, enabling us to make more informed decisions and act with greater precision. The fear of job displacement is being steadily reframed into the opportunity for human reskilling and redeployment towards uniquely human-centric roles. The anxiety surrounding autonomous decision-making is met with increasing emphasis on explainable AI, ethical safeguards, and transparent governance frameworks. The historical narrative of AI is not one of impending doom or effortless utopia, but of a persistent intellectual endeavor, filled with measured progress, unexpected twists, and a growing understanding of the nuanced relationship between human and artificial cognition. We are embracing the continuum of intelligence, recognizing that the future is not about replacing humanity with AI, but about enriching the human experience through a thoughtful and calm collaboration with intelligent systems. In this partnership, the journey of discovery continues, quietly unfolding the next chapters of intelligence, both ours and that which we create.